Hello, my name is Gary Owens, and I'm the Controls Engineer at International Power Technology, or IPT. In this video, I will be reviewing my LabVIEW project. This program was written after discussions with the technicians at IPT and what I might be able to program that would be of value to them. The program is called IPT Engineering Toolbox, and it is meant as a support tool for their field service activities. After the development of the code, it was compiled using the application builder and tested on the technician's service laptops to make sure that it worked. I will now go through the program structure, layout functionality, code structure, and then at the end of the video I will open the executable file and go through the operation of all the functions. For the structure of the code and for layout for the operators, I chose a tab control, container, and different sections of code are organized by specific topics that were relevant to the technicians. Each of these functions were specifically asked for by the technicians. I threw in a few myself that they appreciated. So under instrumentation and control, we have some information to help them with the engine turbine speed control, calibrations, some scaling 4 to 20 interpolations, platinum RTD, resistance versus temperature lookups. Under mechanical, there's a selection where engine components can be inserted in an array and torque values looked up. Under emissions, there's some entries so that you can put raw emissions detected from the stack and correct it to the reference O2s depending on the application. There's a generic conversions tab with some temperature, pressure, and some natural gas volume to mass flow conversions. And finally, there's a procedure documentation tab, which is a place to put small procedures or comments that the operators might need to reference when they're in the field without stopping work and pulling out different manuals. And the code was structured in a way to minimize CPU usage, since all the items in this program are operator entered items. Everything is contained in a while loop that's running continuously. Inside the while loop is an event structure, and to organize the code, I created event cases related to each tab. So the INC tab information is a case, and every item that's can be entered by the operator is set for a value change for operation. So this minimizes the program polling to basically nothing, so that the executable can run without any concerns about resources being used up. To quickly go through the code itself, the speed pickup calibration is using a formula node. It's a pretty simple formula, but the speed pickups are counting different amounts of teeth and gears, and if the operator needs to enter a frequency to verify calibration in a controller, the RPM, it would allow them to do that here. This code here is based around a sub-VI I created that is just a linear interpolation of the current loops that they're typically using, which is a 4 to 20 current loop, which allows them to verify the milliamps are giving the proper process values and vice versa. The platinum 100 RTD resistance versus temperature Actually, there's two formulas depending on if you're above or below 0C. So if we're above 0, we use this formula, and if we're false, we use a longer, more complicated formula. But this allows them to enter the temperature in Fahrenheit, which they're used to, and get the resistance that the RTD should have at that temperature so that they can troubleshoot and verify calibrations. Under mechanical, right now is just a torque lookup. Again, it's set for value change event. This code basically takes the selected value from the drop down and does a lookup in the array to find that part description, and then outputs the element location, and that then goes and pulls out the corresponding torque value in the other array. Under the emissions event, this was done with numerical operations versus formula node, just to do it differently, I guess. So basically, the raw values that the operators would measure out of a stack for the gas turbine or boiler could be put in and corrected to the proper reference O2. Use 15% is the standard for gas turbine oxygen reference and 3% for boilers. This allows them to select whatever correction they need and get the values corrected that make more sense. Under conversions, again, basic formula calculations for pressure and temperature that they typically use and are requested. Like all of these tabs, this is a starting point, and we will add more and more information as we decide what is of use. The natural gas volume to mass flow rate is density correction, basically, and it's currently set for the 14.73 psig, which is the standard density value that Pacific Gas and Electric uses. If things vary too much, we could go in here and tweak this formula. And the last tab is procedures. And for the procedures, we're using a case structure that takes the selected drop-down procedure and outputs the string where that information was entered. The string controls for all these procedures are hidden on the front screen to keep it uncluttered and look the way we want it to look.